Okay, I'm back on the workshop homepage, and here, this afternoon's agenda, we have one kind of longer lesson to go through, which is the intro to machine learning. I'm going to be teaching off the slides, but as usual, there's the full text version of the lesson, which has little homework problems at the end if you're interested. And so I'm going to go ahead right away and download this worksheet onto a folder on my hard drive, which I'll later open up in RStudio. So I'll go ahead and click on worksheet to download the worksheet. I'll save it into my into this folder in my documents here. And then I'll go to RStudio. We won't really be using this right yet because I have a few intro slides, but I just wanted to get everyone set up. I'll go ahead and restart R to clear away all the loaded packages I had and all the variables that were in my environment before. And then I'm going to open the worksheet that I just downloaded. I put it in this folder here, but it might be in your downloads folder or something if by default. There we go. So I'll open that. Okay, so now I'm all set for whenever we actually do the hands-on component of this. But I think this is something that that folks might not know a lot about. What machine learning is. It's obviously a word that people hear a lot nowadays, especially with now we hear a lot about AI, but AI is nothing more than machine learning. So let's spend a little time going through what it is, kind of doing some myth busting about the common misconceptions and that kind of thing before we actually do a little bit of machine learning. So you can see it's not all that hard to fit machine learning models to data and get something interesting out of it. So yes, those are the objectives basically. And after we do the intro, we'll do 2 walkthroughs of 2 basic machine learning tasks using R. Again, you will probably get more out of this if you know a little bit about statistics, because machine learning is kind of just a subset of statistical models. And again, we know a little bit about tidyverse now. I haven't really gone over model formulas too much with you yet, but hopefully if you don't know how to write statistical model syntax in R, you'll learn a little bit about it as we go. And we're going to use the same format as we have been with the worksheets. And yes, I've said this already, but yeah, we're going to look at machine learning, compare and contrast with statistics, talk about using models for prediction versus inference, what that means and why it's important, then get into some of the technical things like training a model and then testing a model on different data sets, what are supervised versus unsupervised, and that kind of thing. And hopefully you'll have a few practical skills at the end of this of how you would go about, once you get some data you want to fit a machine learning model to, how would you pre-process it? And then we're going to use a random forest model to classify data and use lasso regression as another type of machine learning approach. And we're going to learn about cross-validation using the R package caret, classification and regression training, I think it stands for, which will allow you, is very powerful because it can use the same code syntax to fit many different kinds of machine learning models. Once you learn it for one kind of model, you can use it on others. So now, and yeah, this is like a little bit of a lecture, 20 minutes or so, but if people have questions or comments, please feel free to interrupt as usual in the chat or unmute and interrupt. So I wanted to start with a few myth-busting kind of things. And here are the 4 myths that I'm going to go through and hopefully bust for you. Okay, so, machine learning, right? It's kind of like this hyped hot news. I mean, now it's like, yeah, you don't even hear the word machine learning anymore because everyone talks about AI, but it's all part of the same thing. And, you know, statistics, it's been around for a long time. You know, its limitations, what it can and cannot do, are well known. But machine learning and AI are kind of this hotter new thing, and people are coming out and hyping it up a lot without really giving the other side of the coin of what their limitations are, right? And yeah, basically, it's not like machine learning is some powerful new thing that's different or better than statistics. Machine learning models are statistical models, and all models, no matter how fancy they are, whether it's a fit a line to some points or like a neural network with millions of parameters like chat GPT or whatever, those are only as good as the assumptions they make and the data you put into them. Garbage in, garbage out, or good data in, good output out, right? That's yeah, it's no different with machine learning than anything else. So there's no need to be scared of it there. And yeah, some people also might be intimidated by this because it's like, well, these are really complicated and fancy models. It's too hard for me. I'm like established in my career already or whatever. I don't really need to like learn a new trick like this. Well, yeah, in some extent, yes. These are complicated models. To fully understand exactly what they're doing under the hood requires a lot of theoretical background, just like, you know, knowing exactly what every part of your car's engine is doing would be great, but it's not fully essential for you to be able to function and drive the thing around, right? Like there are a lot of software tools out there that make it very easy to fit machine learning models to data. Some ways almost too easy. You can do it without having any understanding of what you're doing. I think striking a balance is best. Like you don't need to know every detail and you don't have to go and get a PhD in statistics and computer science to do this stuff, but you also don't want to just do it completely blindly. Like having a modest level of understanding is kind of where you want to be, right? The third myth is, well, I mean, again, this is another buzzword from like 5 years ago that you never hear anymore, but it's still a thing. Big data. Okay. Some people think, well, yeah, if I have big data, I can do machine learning. But a lot of people in ARS, maybe it doesn't apply as much to people that work with omics, but like I only have small data that I collected in a small controlled experiment. It's not enough sample size. It's not big enough to do machine learning. But I think yes, some of these models really perform best at big scales. These complicated models perform best when you have big, large data sets with a lot of sample size to fit to them. But there are cases where it can be a useful tool to fit machine learning models even to small, hand collected, artisan, whatever data sets. It can still be useful because, well, as we'll get into, machine learning is about prediction, and any case where you're really trying to make predictions on new data, it can be useful to use it, even if your original data isn't huge. And lastly, again, related to the previous, like you might say, well, okay, I'm never going to fit machine learning model to my data, so I don't need to know anything about it. Well, I think that's not true because it's not just hype. It is a very useful approach, predictive modeling and machine learning. It can be useful across all scientific fields. And even, the sort of renewed focus on prediction is changing the way that all statistics and all research is being done, even research that's not necessarily focused on prediction, but focused on inference and learning about how things work is kind of taking a page from this predictive playbook and using more of these approaches. And, this is a topic that you really have to have literacy in, right? Even if you never do it, you're going to be reading about it in the literature. It's in the news and stuff. So it's really, as a scientist, I think you have to have a basic understanding of machine learning and of predictive models in 2025. You really have to. So that's my opinion anyway. Okay, I've said a lot of stuff about what is not machine learning, but what is it? Well, let's define machine learning. It is any job that you give a machine. By machine, I'm talking about mostly computers here, not a lawnmower, a machine to do that it gets better at doing the more data it gets. That's a pretty general definition, right? I mean, you could say a linear regression of weight and height and predict, weight from height by fitting a line is a job you could give a machine to do that the more data it gets, the better it gets. It has a better prediction. So like, yeah, a linear regression with two variables is machine learning by that definition. So you can see it's a pretty broad definition. So we can say by that definition, all statistical models are machine learning models. And it's a machine that takes data as input and spits out a prediction as an output. So yeah, if it works right, the more data you have, the better your model will be at its job, which is to make predictions about new data that it hasn't seen yet. Does anyone have any questions or comments so far? Again, please shout if you do. So when I talk about, okay, a job that it gets better at doing, the more data it gets, well, what are the jobs that we might want a model to do? There's kind of two main categories, regression and classification. Regression would be predicting a continuous outcome from some combination of input variables, like the one on the left, fitting a line through points is a regression. Classification is predicting which discrete category something belongs to based on some combination of variables. So it's not a continuous number we're predicting. It is something with specific discrete levels, categories. Let's talk about classification a little bit more. There's kind of two main flavors of classification, supervised and unsupervised. Supervised classification means we have in our original input data set, we already know which category each of our data points belongs to. Like, we know this individual has a disease and this one doesn't, and here's like the microbiome of that individual A and individual B. We already know. Now, can we predict based on patterns in that data whether individual C has the disease? We know their microbiome, but we don't know if they have the disease. We're going to predict. But we already know for our input data what category they belong to. Unsupervised is we just have a bunch of data. There's no groups that we know about, but we're trying to find kind of natural data-driven groups or clusters in the data, but we have no beforehand knowledge about which group each data point belongs to. That's unsupervised. Some examples, right? So like I just pretty much said the example, supervised would be like trying to predict heart disease from a bunch of clinical measurements on patients, and we know some have it and some don't. Unsupervised would be like a lot of, news aggregators like Google News use an unsupervised machine learning algorithm to categorize news articles that are about the same event. Like, if you if the same terms, for example, like Ukraine and Russia and everything appear in the text of one news article, it's probably about the same event that also has those same words in it. So then it's going to be like under that heading on Google News, a machine learning algorithm actually automatically sorted those things into stories, even though there's no kind of like label of what story any individual or what real life event any individual story belongs to. That's unsupervised. So yeah, supervised learning is great if you can do it. You would want to prefer that if you could, but it requires better quality data. It requires data that already have those outcome labels on it. So some of these like real big data or large scale projects often have no choice but to do unsupervised because they would have to pay somebody, to spend days like classifying a bunch of stories into events to actually have a supervised algorithm work on it. That's supervised versus unsupervised. We're going to do supervised in here in this example because it's a little simpler, but I just wanted to make you aware of this distinction that you may see out there. Yeah, ARS, I just want to shout out to folks in ARS that are doing machine learning models. Of course, folks in MMRU using machine learning to look at the relationship between diet and microbiome and other omics data. There's many machine learning models we can do for that. We'll do some of them tomorrow. Also, a lot of breeders in ARS that are breeding crops and livestock use machine learning models on genomic data from the crops to predict which genome signatures are associated with the traits they're selecting for. Also, a lot of ARS scientists have image data sets, like they fly drones over fields, take pictures, and then can develop a machine learning model to identify which images have weeds in them and which don't, to sort of more target control and fight weeds without having to just spray pesticides and herbicides everywhere. Lots of good use cases in ARS for machine learning. Okay, machine learning is pretty much synonymous with prediction. What is prediction? Well, a lot of scientific inquiry is focused on inference rather than prediction. Inference means finding patterns in the data and using those patterns to understand processes that are going on in the world, like why are things the way they are. Prediction is finding patterns in the data and correctly reproducing those patterns with a model, using a model to sort of faithfully predict real world patterns. And it doesn't matter as much why, what is the true mechanism behind those, what is the true process behind the pattern? If you didn't understand that, you could still correctly predict it, even if you don't truly understand it. You know, I could predict, ancient people could predict the weather based on, you know, signs they observed in nature without truly understanding the physics of clouds and that kind of thing, because there was a statistical association between those things they observed and the weather. That's like all you need to do prediction. Inference means truly understanding why it happens, but we care about prediction. How is more important than why for us in the context of machine learning. So here's an example of kind of like correlation and causation, how that relates to prediction. Yeah, I said you don't really need to know why, but if you do truly understand why things are the way they are, you can make a more robust machine learning model that is more applicable in a wider array of situations, right? Like the classic example is shark attacks and ice cream sales. You know, like if you have a time series of shark attacks per week, it kind of peaks in the summer when everyone's at the beach. If you have a time series of ice cream sales, it also is higher in the summer. And so there's like a high correlation between shark attacks and ice cream sales. So if you like had a model that took shark attack data and predicted when you might sell the most ice cream, it might actually work well. It might actually give you a good prediction, but it's not truly based on a true mechanism, right? Like it's really the time of year or the temperature that the season or something that's causing the ice cream sales to go up and down. So like your model is only going to work as long as that kind of correlation is still present. But if it changes, like if, you know, climate change causes the sharks to migrate to another area, the correlation will break down and it's going to fail. So really, it's better to have your machine learning model be based on variables that have a true mechanistic association, because then it's going to be a more robust model. It's going to have the true causality in it. So like use your common sense a little bit and your understanding of the relationships, not just looking at correlations, right? Because it's going to be a better model and more true to the science that way. I'll take a brief pause to let those big ideas sink in, and if anyone has any questions too, please go ahead.
So Quentin, so if you have
Yes.
more variables, so if you input more variables, then it's better to I know infer that relationship, right?
Yeah. So like you could sort of pre-screen your variables based on which one you have a more prior scientific knowledge to say those ones are probably the ones that have a real causal relationship with your outcome of interest, those would be better to include if you had to choose.
So one more question is like in the supervised models. So so you we divide our data previously, right? Like, into the different categories, right? So
Yep.
um for example, I have in a data and I have to classify my data based on the previous information. So I need to download the previous information and give that also as an input along with my data to perform the supervised model.
Yeah, so supervised would be if we already know what, yeah, you would have to already know what category each of your observations belongs to. Like in your, anytime you have in your controlled experiments that you're doing, it's always going to be pretty much supervised because you know what treatment group all the like samples come from. So like it's going to be supervised. You'll always have that outcome. Yeah, but it's really unsupervised would not apply in your situation for the most part, unless you're getting some external data from somewhere else.
Okay.
Okay, to move on now, let's get into a little bit of very big picture, the math of how some of these models work. Well, any prediction has error, right? Like if you're you can score how well you did at predicting by measuring the error, the difference between the right answer and the prediction we got. And usually that error is represented as a function called the loss function. And we usually want to minimize that value, minimize the error, be as little wrong as possible when we're making a machine learning model. So like when machine learning models are being fit, you're constantly evaluating this loss function and figuring out what model parameters give us the lowest error, the lowest value of the loss function. So like even a simple linear regression fitting y by x line has a loss function. It's the sum of the squared residuals, the sum of the square of the distance of every data point to the regression line. The line that goes right through the middle of the data points has the lowest sum of squares residuals. It minimizes the error. It has the lowest loss function. A lot of machine learning models basically use that same one, mean squared error. That's the minimizing the sum of the squared errors or residuals. So it's exactly the same as a traditional linear regression. Although you don't have to use that. You could also use mean absolute error. Instead of using the sum of the squares of the errors, you could use the sum of the absolute values of the errors, the distance of the data points to the model prediction. That's a little bit less sensitive to outliers because you're not squaring the distances. It just depends on how important you think those outliers are, basically. And classification tasks, because you don't have a continuous variable you're predicting, you can't measure the distance of each data point. You have to use a different loss function. I won't get into them right this second, but there are other versions for discrete outcomes that are different from what you'd use for a continuous variable. So how do we fit a machine learning model? You want to minimize your loss function and get the least error possible, but only up to a point, right? You don't want to overfit the model to the data. Here's an example of if you overfit, like if we took this this trend here, right, and we fit a very complicated polynomial regression with a lot of parameters, we can pretty much make the line go right through every single data point. It has a very low error on all the predictions on this data, but those predictions are just reproducing random noise in our data set. It's predicting the noise in this particular data set. If we try to apply this model to new data, it's going to have a higher error because it's just because that new data is not going to follow that exact pattern of noise in the data we fit it to. But of course, you could also underfit and you could miss actual patterns in the data. The prediction is missing this true pattern where it's kind of flat and then drops if we fit too simple of a model. Like obviously in this case, the sort of sweet spot would be something like this. It captures the overall trend, but it's not fitting every little bit of noise. we're balancing between underfitting and overfitting. How do we do this? We balance our desire to minimize the prediction error with something called regularization. Regularization is anything that makes a model less complex, less specific to the data it's fit to, and more general. And you already do regularization, even if you don't do machine learning. If you've ever done model selection, variable selection, if you've ever fit a mixed model with random effects, that's also a form of regularization. It's saying, okay, we're not going to fit every bit of noise in our data. We're going to like fit the data we have a little bit less well so that we can make sure we're only fitting the true pattern, not the noise, and then we'll do better at predicting on new data. That's regularization. Yes, but that's easier said than done, right? It's kind of hard in practice to know exactly where that sweet spot is. Where is the exact balance between underfitting and overfitting? Well, the way that machine learning approach does it is the machine learning models have what's called a regularization parameter or parameters that determine the optimal level of regularization, where that sweet spot is. We'll show many examples of this as we go. So we fit the training data, the data that the model is fit to, a little less closely, which enables us to get better predictions, better performance on new data that was not used to build the model. How do we do this? I'll give a few more slides explaining that, and then we'll shift to the hands-on portion where we're actually going to do this together. Basically, the way we do it in machine learning world is we have a training set. That's data that we actually use to fit the model, and we have a test set, data that we do not use to estimate the parameters of the model. We just use it to see how well the model predicts on that test set. Ideally, there's complete independence between the training and test set. There's no correlation between the noise in the training set and the noise in the test set. This can happen when they're not independent. That's called data leakage. It's when the random noise in the training set is correlated with random noise in the test set. And that's bad because if you fit a model that's overfit to the training set and just fitting that random noise, but the test set also contains that same random noise, you're going to get an overly positive estimate of how well your model does, and it's going to fail when you take it out to the real world. But there's a limit to how different the training and test set should be, right? Like what we want, there's a term called transferability. We want our model to make the most accurate predictions in new contexts and be transferable from the little world we fit the model to the wide real world. So we want data to test our model that is independent from our training data, but it's still within the domain we want to make predictions in. Like if I'm a crop breeder in Louisiana and fit a machine learning model to predict crop yield, I don't want a test set from Minnesota because it's very unlikely that the model is going to make good predictions there anyway. I might want a test set from, a few miles away from where I trained the model on, because yes, our model is going to be transferable. We don't want it to just fit our data that we built it on, but it's not going to work everywhere in the world. There's sort of a limit to how far you can extend it, if that makes sense. So, but oftentimes we don't have the luxury of having a completely independent test set and training set. So what people often do, this is kind of the best you can do, is if you don't have an independent test set, you have to set aside a portion of your data as a test set. So split our one data set into a training set and test set internally. And the model never sees the test data when it's estimating the parameters. It's only used to test the predictions. And some people are like, well, that's kind of a waste of data. Like, I put a lot of work into collecting this data. I don't want to set some aside and not use it to fit my model, right? Well, you still have to, because otherwise you have no way of knowing if the model is just overfitting or if it is or if it's fitting the noise or the signal. You'll never know. So the model won't be useful unless you have something to test it on. So, hopefully you can strike a compromise. If the data set is big enough, you can only set aside 10 to 20% of it and that still gives you enough data to fit the model on and a decent sized test set. So usually the training set's bigger than the test set. Yes, question.
So I have a question. So it's gonna be true for our actual data too. For example, in a mixed model, like that's a basic model we use, right? Or ANOVA. So we
Yes.
have to do the same thing.
Yeah, so that's a great point, and not that many people do, right? Like it is not a common thing that's done in people fitting statistical models for inferential purposes. The usual excuse people give is, well, we're not doing prediction, we're only doing inference, so it's not as important to us how well we predict on new data. But yeah, I think it could still be good to do this kind of validation on even if you weren't doing a machine learning model, but it's not as important if prediction is not really your goal and understanding the relationships between variables is more of your goal. You don't really need to do this validation. But
Okay.
plenty of stat models are completely overfit the data. So yes, maybe people should do it more, and it would give us more robust inference that was not based on mining patterns in noise in very small data sets. Yeah. I mean, I think you kind of nailed it with that comment, right? Like that's kind of what's underlying the problem of a lot of science not being reproducible, right? Is people overfitting and over explaining things from small data sets that's just random noise, you know? So yeah.
Okay.
But mixed models do a little bit of this like regularization. So like that does address some of the issue, but not completely. So yeah, and if you do split your data set into test and training, you're gonna have to split it in such a way that it minimizes the data leakage as much as possible. Like if you have a geographic sample, you want to like set aside a specific subset of geographically or in time or by category or by block as your test set. You want to stratify the random sample so that you have minimal data leakage, but you also have a representative test set. Um, so sort of taking a step back, before we actually do all that stuff, we want to look at our data and process it and make sure that it's okay and clean before we fit our model to it. Like any modeling approach should start with looking at the data. If you find some data points that are truly invalid, you want to remove them. Removing outliers is a gray area, right? Like if it's really an invalid data point, you want to remove it. But you will not be able to do that later in the real world when you're making predictions on new data. You won't be able to screen it for outliers the way you do the way you can with your training data. So removing outliers is problematic in the machine learning approach. Like we want to make a model that fits the data, not fit our data to the model, right? So yes, if some data are wrong, get rid of them, but it's a gray area when talking about removing outliers. Another important pre-processing step is reducing the number of features. Now, in the stats literature and in scientific fields, you mostly call them predictor variables, the X variables in the model, the inputs. But in machine learning literature, they call them features. So that's just a term you'll see. Now, if we machine learning is no different from any other stat model. We're trying to explain variation in our response by variation in the predictors. If you have predictor variables, if you have X variables that don't have any variation in them, you're not going to be able to use variation in X to explain variation in Y if that variable has no variance in it at all. So like if you had a feature, an X variable that had only 2 ones and the rest zeros out of 1,000, there's like no variance in there. So I would usually remove that before I fit the model. Or if if two features are almost completely correlated with one another, they're not carrying, one of them is not carrying any new information, right? Because all we care about is prediction. We don't actually care which of those two variables is truly the causal factor associated with the response. We can remove one of them, no problem, if they're perfectly correlated. All it's going to do To have them both in the model is going to slow down the model and make it use more memory, take more time to fit. It's not going to make any contribution to prediction performance. So let's get rid of correlated features before we fit the model. Another thing you often need to do before you fit a machine learning model is to standardize your predictor variables, your features, to a common scale. Oftentimes people use a Z transformation. So subtract the mean and divide by the standard deviation, a standardization, so that it has a mean of 0 and standard deviation of 1, so that every variable is on its own scale. Because if you didn't, the model might give more weight to variables that just have a larger magnitude of their units. Like if one is measured in micrograms and goes up to 1,000,000, the other is measured in, a count that only goes up to 5, then it's in totally different units. So we need to standardize. And something that you should be aware of is that you should really do that standardization separately on the training set and the test set to avoid data leakage. You want to base it, the mean that you want to subtract off is the mean only from the training set, and then do it separately on the test set. Now, once we have our data in that form and we've decided what kind of model we want to use, we want to tune the model. That is, estimate parameters based on our training set that will maximize our prediction performance on the test set, the new data that was not used to fit the model. And so some parameters in the model are the ones that actually tell us the relationship between the predictor variables and the outcome variable, like a slope in a regression model. So machine learning models also have like slopes for the predictor variables too. But they also have another set of parameters called tuning parameters or hyperparameters, which I already mentioned before, are special parameters that help us set the balance between overfitting and underfitting. We want to find the value that will get that sweet spot for us. How do we find it? Well, one way you can do it is by what's called cross-validation. We're going to go over this in quite some detail. We're going to do it today, and we're also going to use cross-validation tomorrow in our omics lesson. So this is a good time to kind of fully understand what cross-validation is doing. Cross-validation is when you repeatedly split a data set into training and test sets, and then fit the model on a different training set each time until all data points have been included in the test set at least once. So here's an example. You can do this for any number of folds or groups of the data set, but here's an example for 5 equally sized folds. So here's what we do. We divide the data up into 5 equal groups, call them 1 through 5, and we fit our machine learning model to folds 1, 2, 3, and 4, not using 5, and then we use that model's parameters to predict the outcome for 5. Then we do the same, fitting it to 1, 2, 3, and 5 and predict 4. Then we predict 3, 2, then we predict 1. So we actually fit the model 5 times, each time to a different 80% of the data until we have a prediction for the entire data set. We do that entire process for one combination of values of the tuning parameters. Then we do it all over again for another combination of values of the tuning parameters, the one that strike the balance between overfitting and underfitting. And every time we evaluate the prediction error on this data set, and then we find the tuning parameter value that minimizes the loss function that has the best prediction performance to fit the final model. So you can see this is computationally very intensive, because let's say our tuning parameter is, varies between 0 and 1. We'll fit the model 5 times for 0.01 for that parameter. We'll fit the model 5 times for 0.02, 0.03. You're fitting the model dozens, hundreds, thousands of times. So it's computationally very intensive. Luckily, we have very fast processors and a lot of memory that we can use for this stuff. And also, you might have to repeat that entire cross-validation process many times, because if you just split the data in one way, you might by chance get an especially high or especially low prediction performance. So we want to do many random splits of the data into 5 groups, not just one, and repeat the entire process over again. And another thing to note with cross-validation is if you have any blocks or random a blocking structure in your data, like if you have crop data from different fields, or if you have data from different states or something, you don't want to split up those blocks into more than one fold, or you'll get overinflated estimates of model performance. You're actually, again, you're fitting on the random noise and not on the actual signal in the data. So you want to keep the blocks separate into folds when you do, if you have cross-validation with blocked data. Any questions on this so far? Excellent. Now, once we've done our cross-validation, okay, we've cleaned our data, tuned the model, found the optimal tuning parameters. Now, and so all of that we did on the training set. We've had a test set that we've set aside and never let the model see, even in any of that cross-validation at all. Now we fit our final model to the entire training set using the optimal tuning parameters that we selected by cross-validation. And now here comes the moment of truth. Let's validate the model on data that it's never seen before. We come back, get our test set that was originally split off at the beginning, and evaluate the model's prediction performance on that test set. Did we do good enough? Well, it depends on what good enough is defined as, right? There's no P is less than 0.05 statistical significance threshold. You know, what is good enough? Like, is it good enough to get within 1% of the truth? Or is that terrible? Like, do we need to get within 0.01%, or is within 10% good enough? That's a practical question, right? That's not I cannot answer that for you as a statistician. That depends on your needs, right? If you're a business trying to make money, it's like you want to get in close enough to make money, or like if you're trying to assess disease risk or something, how often is it okay to be wrong about that? That's a practical question. So this just recaps what I just talked about. We're splitting the data into training and testing sets. Put that testing set in a locked box and don't look at it again for a while. Within the training set, we're going to do cross-validation, dividing it into smaller sets to tune the model, find the optimal parameters, and then get our model that should be pretty good and fit it on the entire training set, and then validate it by making predictions on the test set. And I did mention that the main goal of machine learning is prediction, but we can also use them to some extent to make inference as well, and to understand why things are happening, what variables are actually driving the prediction, and there are different methods that exist to quantify that. I'll show you an example of it in our hands-on demo, but that's not really a main focus of the lesson, but there are a lot of ways you can do that. But again, it's not based on a true mechanistic understanding of why this stuff's happening. It's still looking at correlational associations between variables. And then once you do that, what you do is you do it all over again, right? Like, that was all for just one class of machine learning model. There are literally thousands of different algorithms, different machine learning models out there. Again, all we care about is how well they do at prediction. So we can do as many different ones as we want. We can use neural network, random forest, boosted regression tree. There's all these kinds. We can try out a bunch of them and see which one works best. Like, as long as you use the proper regularization to prevent overfitting, you can just use the one that works best, even if it wasn't the first one you thought of or whatever. But I do want to point out there are some really complicated machine learning algorithms out there. More complicated is not always better. I think you want to strike a balance between a good prediction performance and at least kind of being able to understand what it's doing. Otherwise, it might come back to bite you if you really don't know what your model is doing. So yeah, this slide, Bharat anticipated that with his question. Why don't people use this training and validation workflow in conventional statistics. I think they kind of should. I already said this. Overfitting is a problem, and science. A lot of published science is actually based on random noise that is statistically significant in a small sample and is not a true meaningful association between things in the real world. And some of these putting models to kind of a harsher test and actually externally validating them on new data, like if you really think you're right, why wouldn't you subject your model to the harshest test you could come up with? Because if it survives that, you actually are onto something, right? And so that is good both for prediction and inference, I think. So yeah, that was a great question before. Couple more notes before we dive into the hands-on stuff. Yes, question.
So, Quinton, can we do the cross-validation on our own data using, conventional statistics?
Yes, you could. Yep, you could use cross-validation on any statistical model you want to. Yep.
So
I
there is
mean,
any
it's just a matter of
specific,
writing the code. Yeah.
if there is any specific models we have to, or to verify our model is good, or to verify our results are good,
Yeah, I mean, you could use cross-validation, or you could use data from, if your lab has been around for a while, right? You have like data where you did similar studies at different times. You could use data from one and try to predict from another, or use a model fit to one run of the experiment and try to predict from another run. That would be a good test of it. Yeah.
Okay. So for
But yeah,
example,
I mean, go ahead.
So for example, like we run our experiments in a trials, right? Like trial 1, trial 2, trial
Yep.
3. Can we use the model which we used in the trial 1 to predict for the trial 2?
Yes, that would be a good example, right? Because like if the pattern is truly general, if there's really a mechanistic association between that predictor and the outcome, it should exist regardless of the random noise between the trials. So it would be a good test of the validity of it if a model that was fit only to trial 1 had a good prediction performance on other trials. Yeah, that would be a good example. Yeah, so it can be done. Yeah, I mean, we could write code to do cross-validation on any data set we want, or any type of statistical model, even just a simple regression. So yeah, I just want to point out another thing about software. We're using R here, but a lot of people, like you may have heard of Python, is very commonly used by people in the machine learning field, and some people think is the best for machine learning. But I think even SAS as well also has good machine learning functionality and good libraries. So pretty much it doesn't matter, because all the main common algorithms you'd want to use are written in all these software. So you can use whichever one you like the best, I think, and it'll work fine. And here's a couple of caveats before we get started. So I mentioned this already, that there's like, sometimes it's almost too easy to fit machine learning models, like, oh, just give us your data and here's the result. You don't even have to think about it. I think in one hand, it's good because we don't want to have like a lot of barriers to entry. We don't want people to have to be like really good at coding to be able to work with these kind of models. But again, I think especially in the era of language models, AIs that are giving people code they don't know what it's doing, it's dangerous to get results without an understanding of how you got them, because then you don't have the knowledge to verify if it's good or bad. I think there's no real substitute for looking at the data and customizing a model for your particular situation. And that's part of the reason I did not decide to use the tidy models package, which is used in a lot of intro machine learning and R tutorials, because it takes away too much of those decisions from the user and puts it behind the scenes. And then I think it takes away some of the understanding. It's good for when you know more, it's more efficient to skip some of that stuff. But I think when we start out, we need to do it explicitly. Otherwise, you'll never learn. I'm not going to make you do it with pencil and paper, but we got to strike a balance somewhere, right? And yeah, this is my big picture slide. basically, I just want to, you may have heard of mixed models and you may have heard of Bayesian statistics, and we're talking about machine learning now. Well, I think they all seem different, but have this common thread. Machine learning uses these regularization and tuning to help you not overfit your data, not fit the noise, and make general predictions that apply everywhere. Mixed models use random effects to not overfit to your data and make more general predictions. Bayesian models use something called prior distributions to not overfit to your data and make more general predictions. Because that's what science is, right? It's making general predictions about the world, and they're all kind of doing the same thing, and they're all good tools to use. The more you know how to use, the better. And there's a lot of overlap. Like we can do Bayesian machine learning with random effects if we wanted to. They're not mutually exclusive. So that was the introductory portion. We're going to spend the rest of the time doing some hands-on stuff. Let's take a quick 5-minute break, bio break. It's 2:07 Central by my clock. So let's come back at 2:12, or well, now it's 2:08. Let's go come back at 2:13 and continue. I will step away for a moment, but I'll be back in just a second to answer questions if anyone has any in the break. I'll be right back. So we'll get started again in just a minute or so. Okay, so hopefully everyone is back, and we will start the rest of the time. We're going to be doing two hands-on machine learning demonstrations coding together in R. And I will intervene and explain some more background about the specific type of, since I gave you kind of big picture so far and haven't talked about how any specific machine learning model works, we'll have to kind of explain that a bit as we go. The first machine learning model we're going to do is to take data gathered by taking photographs and measuring things on the photographs of different dates, like the type of fruit, and using that to try to predict what variety of date it is that you have a picture of in front of you. Something that you've always probably wanted to do. I got this data set from a website called Kaggle. That is a site that hosts a lot of free example data sets. And they have these like competitions where they'll put up a data set and say whoever can make a machine learning model with the best prediction performance wins. And you know, it can be, I guess, good for junior people to build their resume by doing those competitions. And it does have a lot of data sets from ag science. And this data set was put on there, and that's you can download and use them. And what we have here is about 900 dates, fruit of the date palm, from 7 different varieties. A photograph was taken of each one, and image analysis software was used to take 34 different measurements, the same 34 like length, width, circumference, and that kind of thing on each one. And so each row of data is all the data from one fruit image. We have 35 columns in the data, 34 measurements, and one column indicating, it's called class, indicating the variety of date that we have. What are we going to do in this demo? We're going to import the data. We're going to look at it, clean it up a little bit, standardize it, do our training test split like I've been talking about. We're going to fit a type of machine learning model called random forest, and we're going to use cross-validation to determine the optimal value of the tuning parameter of the model, and fit that model on the full training set, and then look at our accuracy on a test set. Just like I've been explaining, but we're actually going to do it now. Okay, let's go into RStudio, open the worksheet for this lesson. And then the first thing we're going to do is load the R packages that we're going to need for the lesson. Now, here's where hopefully you went through and installed all the needed packages earlier. Otherwise, you're going to have to actually install these packages before. Otherwise, you won't be able to load them. So hopefully everyone can do that. And if you can't, hopefully Grant will be able to help you. And once we've loaded the packages, we're going to import the data from CSV, which I put on the website, so it'll just be downloaded directly from there. And then, yeah, you see it's got a little pipe like we learned about this morning to mutate class into a factor variable, right? Because class is a text variable, but it can only have a few specific levels, so it's easier to work with if we convert it to a factor. That's what we're going to do. So let me go to RStudio. I've opened up my worksheet. I'll highlight this block of code with all the library calls in it and hit Control Enter to run it and load the packages. So we're loading tidyverse, we're loading some machine learning packages and some some plotting packages for visualizing the data. And yes, unfortunately, I forgot I didn't update this worksheet to have the URL, because in previous versions of this lesson, we were working off of a demo server that had the data in a folder called data, but you're going to need to go and change from where it says data to use this. This should be instead of we'll copy this. Instead of data, we're going to have to use this long path here. Again, here, I'll just I'll put that in the chat as well so people can copy that without having to go find where it's at. So yeah, there's that. Sorry about that. Yes, we're going to use the read_CSV function to import it, which we've already seen before. And we're going to turn class into a factor variable, capital C class. So we'll read in that, import the data, and then convert class to a factor. So I'm going to hit Control Enter, and that'll do its thing. And if this worked for you, you should read in about 900 rows and 35 columns. If anybody is having trouble with that, either let me know or hopefully Grant can help you. Let me make a note. I have to edit that worksheet for next time. Okay. Yes. Again, if you are having trouble, please don't be shy and let me know. I don't want anybody to miss the fun stuff because they can't get the data loaded in. We're going to take a look at the data. We want to know how many rows and columns we have, and we also want to know how many of each of the classes are in the data. So we're going to use the table. We're going to use the dim function, which gives you the dimensions of the data, the number of rows and columns, which we already saw, but I just want to show you another way of looking at that. And the table of this $ class means we're going to take the class column from the data and give me a table of how many times each value appears in that column. We want optimally a pretty good balance, and so that we have a decent number of all the varieties we're trying to predict. So we go to, we'll use dim to look at the dimensions, Control Enter. Just as I said, there's about 900 rows and 35 columns. We already saw that. And then we'll use a table to look at the how many of each class. So you can see there's 7 varieties that have different names, and there's a decent number of each. You know, some have 200, but the lowest is 60. So that's great because we want our training set and test set to each have a decent number of all the varieties. And so there's enough there that we can have a good amount of each variety in our training and test set. Now, let's start exploring the data a little bit. We're going to plot all the yes, it says response here, but I mean to say predictor variables as box plots grouped by class. So we'll have a box plot of the distribution of each of these measurements by date variety. And let's take a look at whether we can see any patterns. What does the distribution look like? Are there any weird data points? And we're going to do this by first, we're going to pull out all the column names except for class. That's what this line is doing. It means give me all the column names besides class from this data, because those are all our predictor variables. And then we're going to do a pivot longer to turn it into a long form for plotting. You've seen pivot longer already. And then ggplot, we're going to plot is a function that is used to plot the plot, in every case, the class on the x-axis and a box plot of the value on the y-axis with some various options. And yes, so the only blanks I've left you is we're going to use a pivot underscore longer to make it into a long form. And the columns we're going to pivot are all of the predictor variables, predictor underscore variables. And I can hit tab to complete that name that I started. So I'm going to highlight this entire block and I'm going to run it. And it's going to make a plot with a whole bunch of little panels. Let me zoom in on that. So yeah, what do we see? Well, you all can see that, right? Filling up the screen. So we have different things like, I don't know what something like area, how large is the date? Well, some varieties are bigger and some are smaller. Like there's pretty good separation of the varieties here, right? But just area is not enough to distinguish all the varieties, right? Like this Berhi, the red one, and Iraqi, the bluish green one, are both big. So if we only knew area, we wouldn't be able to tell them apart. But they might differ in other aspects, right? Like I don't know what some of these things are, but they're all various relationship between the area, the length, and the width, and that kind of thing. The major axis being the length of the longest diameter, and some are rounder and some are more long and skinny. We do notice, here's a weird one, the aspect ratio. It looks like they're all pretty low, except one is super high. It's like 500. That seems incorrect to me because aspect ratio is the ratio of length to width. Dates are more or less circles, so it should be pretty close to 1. 500 would be something 500 times longer than it is wide. That doesn't seem correct. So that seems like not a outlier in the sense of an extreme value, but an outlier that's just plain wrong. And so I would say let's get rid of that data point and just delete that row of data from it, because we don't really know if anything in that row is correct. And so, yes, the simplest thing to do here is just filter and say aspect ratio less than 500 to get rid of that one row where aspect ratio is greater than 500. And then we'll look at the number of rows to see how many we have left. So aspect underscore ratio in all capitals is the name of the column. Less than 500, we'll filter it by that. Control Enter. Then we use the n row function to look at how many rows there are left. So it only got rid of one. We had 898, now we have 897. So that's good. We've gotten rid of a sort of wrong value. Now, I told you before that it's good to get rid of predictor variables that are highly correlated with one another. We're going to calculate the correlation coefficient between all pairs of those 34 variables. And then this GG core plot is a function that makes a correlation heat map, so we can say which variables are correlated more highly with one another. If any of them are close to 1 or -1, we could get rid of one of the two in that pair, because they're not going to give us any more information if we use both. Oh, and we use the core function to find the pairwise correlations between all the predictor variables. The COR function. So we'll run this line to get the pairwise correlation matrix. You can see it's a 34 by 34 matrix, all the pairs of correlations between those 34 predictor variables. And then we'll use the GG core plot function, which we loaded the library for. And type equals lower will give us just 1/2 of that symmetric matrix as a heat map. And I'll zoom in on this again so you can see. So yeah, if a correlation is close to 1, that means those two variables are almost perfectly positively correlated. If it's very dark blue, they're perfectly negatively correlated. So, your perimeter and area are fairly highly correlated, for example. Some of them look like they're pretty close to +1 or -1. So we actually should be able to get rid of a good number of these variables. So let's go ahead and do that. Now, there's a convenient function in the caret package, as I told you, is kind of this sort of overarching machine learning package called find correlation, which will identify any variables that are correlated with at least one other variable in the data set above some threshold. Now, I've used 0.95 as the cutoff. You could use a more or less strict cutoff depending on what gives you the best performance. But if two variables are 95% or more correlated, then they're almost on a perfect line at that point, and one is good enough as both. So find correlation function will do that, and then we can use the select function, which I told you in this morning is used to select columns of a data frame. If we use the minus sign on select, it will delete columns, and so we can select minus sign all of correlated variables. That will delete the columns containing those correlated variables from our data set, and I'll assign the result back to date fruit. So now we're going to have less columns than we started with by getting rid of some of those correlated features. That's what we're going to do here. Find correlation is the name of the function there, and cutoff is 0.95. We'll run that. You can see correlated variables in our environment pane. We can see there's 16 of them. So we're actually going to get rid of half the variables in the data set here are correlated with at least one other one at 0.95 or greater. If we say select minus all of, and then we'll use that, pass in that correlated. I can hit tab to complete that. And then if I run that line, control enter, now you can see date fruit has a lot less columns, 19 of them. We got rid of quite a few columns. Any questions on this so far? Yes, Manoj.
Hey, Quentin, I'm just wondering, like, do we know like what kind of correlation is calculating?
This is just doing a Pearson correlation coefficient. Yes, we can look at if you look at the documentation of find correlation.
Yeah, I'm checking that and I don't
Yes.
see.
Oh yeah. So I actually passed in this correlation matrix I already made. The COR function by default does a Pearson correlation. We could change that by supplying an argument method. If we wanted to do like a rank correlation or anything like that, we could do it there. That's where you do it.
Okay, yeah, thanks.
Yep, yeah, that's right. Find correlation uses the correlation matrix I already created, which that's where you would decide what. That's where I did Pearson because that's the default there. Yep, good question. So now, as I've said in the intro slides, we want to split up our data into training and testing. And in this example, I just said where we're gonna take 90% as training, use that for the tuning of the model, and 10% we're going to use later to evaluate how well we did. The caret package also has a function called create data partition that will do this automatically in a balanced way for us. We want to roughly take 90% of the data from each of the varieties in the training set and 10 in the test set. If we just did a straight random 90 to 10 of our data, it might leave out one variety entirely from the training or the test set. So this stratified random sample ensures that we have roughly 90-10 split in all the varieties. And that's what this is doing. and I've set the random seed so that we will all get the same results of our model, regardless of how. Or yeah, if you set a different seed, you would get a slightly different result because it split things up a bit differently. And we're going to create data partition by this class column. P equals 0.9 means we're going to do a 90% by 10% split. And yeah, the list equals false means we want to return a vector of training indices instead of a list. And then we'll use our date underscore train, create a data frame. And remember, if we use brackets to select rows, we can select rows based on this train index. And if we put a minus sign, that means we select rows that are not in train index. And so date train and date test will each have a lesser number of rows than the original data frame. There'll be a training subset and a testing subset. So let's do that. We'll do our create data partition. The column we'll use is class with capital C. We'll use 0.9, 90% as training. And we'll call that train index. So let's run that. Set the seed as 1, run that line, then run this line. You can see train index has 811 is 811 rows in it. Those are the row numbers that will be in the training set. It's about 90% of our data. Date underscore train is the name of the smaller object we're going to create for the training set. And so we only want to keep the rows called train index, capital I. And date underscore test is what we're going to call the test set. Train index there. Okay. And so I'm going to run those two lines there, highlight them and run them, Control Enter. So you can see date train has 811 rows, 19 columns. Date test has 86 rows and 19 columns. So it's roughly a 90-10 split. We're going to now use cross-validation to tune a random forest model on the training set. But I'm going to take a step back and spend a few minutes explaining to you what a random forest model is and how it works, so that you have a better understanding of what we're doing. It's not just a black box to you. So yeah, what is a random forest model? Well, it is a model. The algorithm is it randomly samples the data with replacement many different times and fits a decision tree to each random sample. Okay, that may not make any sense to you, so I'm going to explain what that means. First, by saying, what is the decision tree? Well, a decision tree is any way of sequentially splitting up a data set with a series of rules that ultimately lead you to the class or value as the outcome. Like this is an example of a decision tree for classifying animals. Like, okay, we've got our animal. First, we ask, does it have more than 4 legs? Yes or no? If we say yes, then we say, well, does it have more than 6 legs? Yes or no? If yes, it's a spider. If no, it's an ant. Obviously, this is very oversimplified, but that's the idea of it. You know, if it does not have more than 4 legs, yes. Does it have feathers? Yes. Well, is it red? Yes, it's a cardinal. And if it doesn't have feathers, it must be a mouse, and that kind of thing. That's all a decision tree is. It's a series of splits that allow you to classify an observation into based on the outcome. That's all it is. That's all this model is doing under the hood, is just doing a whole lot of those decision trees. And just like for our dates, it'll be like, is the circumference greater than 30 centimeters? If so, it could, is it like wrinkly or not wrinkly? Yes or no? And then that's exactly what it's doing under the hood. It's called random forest because it has a lot of decision trees, right? It's a forest of decision trees, and it uses a majority vote across all those decision trees to make the final classification rule. And it's called random forest because it randomly samples the data with replacement and fits decision tree to that random sample. And every time it does a random sample, some data points are selected for that random sample. They're called in the bag, and some are not out of the bag. And the algorithm basically, I'll skip over the details. It bases its final model parameters on the tree's prediction performance for the data points that are not selected out of bag for each tree. So it already is kind of internally doing a little bit of a training testing split. It's fitting the decision tree to some of the data and predicting the rest, and doing that a lot of times. So it's already regularizing within itself, but we're even going to go one better and do cross-validation on the random forest. So even every time we fit the random forest, it's splitting up the data. Then we're going to use cross-validation to split it again, basically, just to like be extra conservative and make sure we're not fitting the model to noise and fitting it to true patterns that exist in the data. So how are we going to do it? We're going to use the carrot package, an R package that is used to train machine learning models. The main function that is used for most of this in carrot is called train. Train being a machine learning term for estimate parameters of a model. And first, we're going to specify what method are we going to use to train the model to find the optimal tuning parameters. We use train control function to specify that. And we're going to say we're going to use method equals CV, stand for cross-validation, number equals 5. We're going to do 5-fold cross-validation. Split the data up into 5 groups. You could use 10, or you don't want to go too much less than 5, because then you would be fitting the model to too small of a data set each time, and you don't want to go too high because it would take forever, because you have to fit the model 5 times for every combination of tuning parameters. You don't want to split it up into 100 groups, because then you'd be fitting it 100 times. So it's kind of somewhere in the 5 to 10 range is good. And we're going to assign this train control outcome to a variable called CV spec for cross-validation specification. So we're going to say train control. We're going to call it CV, where the method is cross-validation, and we're going to do 5-fold cross-validation. Run that line, and now go back to the slides. Okay, I've set the speed to this number just to get a specific result. This is the train function, and now this is kind of a lot, right? We've put a lot of arguments to the train function because it is basically the entire model fitting process is encapsulated in this one function with 9 or 10 arguments that I'm going to walk you through each one. It has a formula, what data it comes from, the method, and so forth. So let's walk through that. Form is the model formula, and it's class tilde dot. That means use all other variables in the data to predict class. So we don't have to write out every variable. We use this dot as a shorthand. That means class is our thing we're trying to predict, and we're trying to use every other column in our data to predict it. The data argument tells us what data frame we're fitting the model to, and we're going to use our training data for that. Method equals RF is the argument telling it to fit a random forest model, and the random forest model itself is actually in the R package random forest, which we also loaded in our R session at the beginning. There's a lot of other models here. I put a link in these slides. You can go to the slides and click on this link to see all the other models that Carrot supports. It probably supports 100 at least different models. This pre-processing equals C center comma scale. Means we want to do a Z transformation, a standardization of all the variables. We're going to center them. That means subtract the mean and divide by the standard deviation. So we're doing a standardization on all the variables. Like I said, because they're in different units to begin with. This will standardize them so they're all comparable. Then, keep going through all these many arguments of train. Tune grid is a data frame with all combinations of tuning parameters for the random forest model. Now remember, tuning parameters are used to set the right balance between overfitting and underfitting. The random forest model really only has one important tuning parameter called mtry. That's the number of variables that are randomly selected each time a new split point, a new branch in our decision tree is reached. The higher it is, the closer it fits the data, but that means the more potential for overfitting there is. If we're willing to consider more variables when we're making the decision tree, it's going to fit the data closer, but it might overfit. We want to find the right balance there. If we do too low, it might underfit. Metric equals accuracy. Now remember, we talked about a loss function a while ago. Accuracy is our prediction metric. And here we're actually maximizing this value. The overall percentage of correct classifications that we get from our model is what we want to maximize, which makes sense. We're trying to predict a categorical variable, the type of date from the measurements. So we want to be as accurate as possible on that. And the TR control is where we pass our object we created before that's telling it to do 5-fold cross-validation. nTree is an argument to the random forest function, the number of trees in each random forest model. And basically, you can set that as high as you want, but the higher you set it, the better performance the model will have, but it will take longer to compute. So I think I set it to 500, which does well enough. You can play with that number and see how it affects the results. Lastly, importance equals true. I wanted to calculate variable importance values, showing how much each variable contributes to the prediction performance of the model for us to look at later. So going back, okay, these are all the arguments. So that took a while to go through. Formula is class by everything. Date train is our data set. We're going to use random forest. We're going to center and scale. We're going to try out all values of mtry between 1 and 10. We're going to maximize our accuracy, do 5-fold cross-validation with 500 trees, and look at variable importance. So let's type all that into the R code and then run it. So I've left it all blank so we can really understand what it is we're doing. So class tilde period, using all variables to predict the date variety. Date underscore train is our training data, 90% of the data that we're going to use to tune the model. RF, we're going to do a random forest model. We're going to center and scale the data. That means standardize all the variables. We're going to use mtry equals 1:10. We're going to try out 10 values of this mtry parameter, see which one gives us the best performance. Our metric is accuracy with a capital A. And we're going to use this CV underscore spec that we created, which is telling us to do 5-fold cross-validation and 500 trees. If you missed some of that, you can go to the text version of the lesson or the filled out worksheet and copy and paste that code if you miss some of that. So yeah, now if my cursor is somewhere in there, I'll hit Control Enter and run that entire thing. Oh, and then the entire thing is going to be assigned to an object called date random forest train. I'm going to hit Control Enter and run it. It should just take a minute or so to run. But it's doing many, it's fitting the whole thing 10 times, and each time it's fitting the model 5 times. And within each of that, it's doing hundreds of trees. So it's doing quite a bit of computation. So it might take a minute or so to run. Okay, so mine is already done. Now we're going to spend the next little while looking at this model and seeing how well it did. Yes, does anyone have any questions or comments before we go to that next thing? Okay, so
I have a
first of
question,
all,
but it's
yes, go ahead.
Quentin, I have a question, but it's gonna be very basic, and I think I missed
No
somewhere
worries. No worries.
in the starting of the code. In the correlation, right? Um, in the code, there is says like I think line 45. It's date underscore correlation, right?
Here, yep.
Um, so here you says like in the column is the predictor variables, right? So we have created that that's a characteristic vector, right?
Yep.
Previously we created
Yes.
so
Predictor
when
variables is 34 names of the columns.
so here is the question is like when we created the characteristics, right? So basically it also saves the data under the each character. Like for example, the area, like the data under the area for
Um,
the
so
column.
the object predictor variables is only a character vector, predictor underscore. If I type that in and hit enter, it's just the names. All this is 34 text values. But if I here
Excellent.
date fruit bracket comma predictor variables means take that date fruit object and give me those 34 columns with those names. So yeah, if I hit Control Enter on that,
Mhm.
oh well, oops. Now I've already gotten rid of some of the columns. Now date fruit, I overrode it with fewer columns. So now I can't subset it anymore because right, I already
Yeah, yeah,
some of these
yeah,
columns no longer exist in the data. So I've tried to go back, but I can't at this point. I'd have to
yeah. This
reload it from the beginning. But then COR function takes a matrix of data and calculates the correlations between all pairs of columns in the data. So since the data have 34 columns, it's going to calculate the correlation coefficient between column 1 and column 2, column 1 and column 3, all pairs. So it gives us a 34 by 34 result.
yeah. I have one more question. So if you remove the class from the data, so then we just put the correlation in the bracket date underscore fruit. It also generates the
Yes,
correlation
that would do it
matrix.
also. Yep. Yep.
Okay.
This is giving me, yeah, I mean, since predictor variables was every column besides class, that would give us the same result. Yes.
Okay. Okay.
Yep.
That's it. Yeah.
Thanks for the question. So yeah, so let's see, where were we? Well, we're trying to look at the model performance. Well, you can use the plot function, which will call up a basic plot of the prediction performance of our prediction metric for every value of the tuning parameter that we use. So I'm going to hit Control Enter and take a look. So here's the plot showing our cross-validation accuracy based on the M-try, the number of randomly selected predictors. Well, you can see, hey, it kind of goes up and down, but wait, look at the y-axis. It only is going between 0.892 and 0.886. So like the worst performing one was 88.6% of the time correct, and the best performing was 89.2% of the time correct. To me, I mean, there's no formal test of statistical significance here, but practically speaking, there's really no difference there, right? So it seems like our performance is not very sensitive to the choice of this tuning parameter. It's basically the same performance. It's about 89% correct the whole time, right? That's what I would say. If we just type the name of the model object into our console and hit enter, which I'm going to do here, you also get some fit statistics from the model, which I'll show you. So here we can see this is just like the same. These are the same accuracy values that are in the plot, except just in a numerical format. There's also this other loss function called kappa, which is just a different way of weighting the accuracy. Gives you slightly different number, but a similar pattern. It's all about the same. The final value used for the model was m try equals 4, right? That gave us a tiny bit better prediction performance than any of the other ones. So it said 4 is the best. But again, we could have really picked any and it would work okay. Because random forest is a pretty good algorithm that is not that sensitive to our choice of tuning parameters. So we actually can be happy with that it didn't change a lot depending on how we set that. Another way we can summarize our classification-based machine learning model is a thing called a confusion matrix. A confusion matrix is a matrix showing the true and false predictions of the model. And the function confusion matrix will give us one. The rows are the model predictions, and the columns are the truth, the right answer from the training set. 100% accurate model would have the diagonal of it, where prediction equals reality, would not be 0. Everywhere else would be 0. I'll show you in what we get if we use confusion matrix on our if we call that on our training the fit model object, date RF train. So here it says that a cross-validated 5-fold confusion matrix. Entries are percent average cell counts across resamples. So if, looking at the columns, if the true variety was Berhe, the model, this is how often out of all samples the model predicted Berhe. And it very rarely predicted Berhe for things that were not Berhe, right? So it was right a lot more often than it was wrong. And same goes for like, for example, Safavi. The model never predicted these varieties if the real one was Safavi. It a couple times predicted Sogai, but usually way more often than not, it was right? Because we were right about 90% of the time. So most of the positive values are on the diagonal, and a few are non-zero entries off the diagonal. But overall, this looks decent. This is something you might present, say, in a manuscript showing the results of a machine learning model. Okay, well, that's great, but that was all just the cross-validated accuracy. Well, let's test the model on a new data set it's never seen before. So even though we don't have a truly independent data set, we just created this so-called independent data set by subsetting our original data set 10%. But at least those specific data points were not used to fit the model at all. So we'll use the predict function, which can be used on caret models, and that will make predictions on the test set. And it has 2 arguments: the model that we're using to predict, and the new data we're going to try to predict the categories off of. So we're going to give it the measurements for the test set and ask it to predict the classes for the test set. And the data that we pass, the new data, has to have all the predictor variables that were in the model be in it. And then we're gonna make a object called date predict test, and then we're gonna make a confusion matrix comparing the predictions with the class column from the test data set to see how often we're right. How is the accuracy on this test set? This is like our validation of the model. So we'll use the predict function, and then we'll use our date underscore test as the new data. Run that. And it gives us a factor vector, which is like the predictions on the date test data set. Then we can call confusion matrix on that, on our vector of predictions and our vector of truth, the right answer. So this is what our model predicted, and this is the right answer. We're going to run confusion matrix on that. And here's what we get. well, yeah, it gives us a bunch of fit statistics. But if you scroll up, you can see the confusion matrix. This time it gives us, instead of percentages, it gives us integers. So you can see, oh, and here's the accuracy. It actually did quite well. It did just as well as our test set, actually. It gave us 89.53% of the time we were right. And it even gives us a 95% confidence interval on that and a no information rate. That's like how often would we be right if we were completely randomly guessing? It would be about 23% of the time. So, and we were right about 90% of the time. So that's pretty darn good, right? Like it, if the true one was, for example, Dokol, 19 out of 20 times it predicted Dokol, and only 1 out of 20 times it predicted another variety. So we were right a lot more often than we were wrong. So this model is a well-performing model. Now, I'm not sure if this, with these data sets you get from the internet, you never know if they artificially cleaned them up to make it work really well, or if it's based on simulation and not reality or anything like that. So I don't know if this is kind of the performance we would expect from real data in the real world, but I'm giving you a nice clean example here to work with. Back to the slides. What else are we going to do? One other thing you might want to do, now that we've kind of shown, hey, this model is validated, it works well. Now we can say, not only use it for prediction, we could also try to explain why we got the predictions we did. What attributes of those images were the most influential in helping us separate out the varieties? There's a since we put importance equals true on it when we fit the model, it calculated some extra numbers in the background that we can then use to score the predictor variables and tell us which ones were the best at reducing the error. And it gives us what's called a mean decrease in accuracy. So it says for each variable, if I took it out of the model, how much did my error rate increase percent-wise? So the higher that is, the more important the variable. If taking that variable out made the error go up a lot, it was obviously important for our predictions. If taking that variable out didn't change the error, it barely made any difference to our predictions. And var imp is our function for that, variable importance. Type equals 1 gives us importance overall. You could also do it for each variety, which variable was most important, but type equals 1 gives us them overall. Scale equals false gives us the raw importance values, not scaling them out of 100. You could also, but they'll have the same interpretation either way if you're just looking at relative importance. So let's take a look. Var imp with a capital I is the name of the function. We're going to use our fitted model object, type equals 1, and scale equals false. And hit Control Enter. So you can see here the variable importance. Area is the most important one. If we took that variable out of the model, it would make the error rate increase by 50%. So that's, the size of it is, we saw that from the original plots, like some are big and some are small. So if you know the size, that goes a long way toward knowing what kind of date you have. And then there's, entropy, which I guess is like how wrinkly it is or something, that makes a difference, how compact, how round, and so forth, whereas some are less important. So that can be something that's interesting or informative to you. Yes, I have a couple more things on this model, then we'll take a quick break and spend the rest of the time doing one more type of model. But so yeah, does anyone have any questions? I'll do just a couple more minutes before we take a break. Does anyone have any questions now? I know we've been going at this all day. I admire you all for sticking with it this far. Hopefully you're learning something still. Yes. Now, this next part, I just wanted to show you how easily, too easily in some ways, we can just adapt the train function we already wrote to fit another machine learning model to the same data, basically with only tweaking a few arguments, we can just do an entirely new machine learning model. This time I went through random forest and explained to you, how it works more or less. I'm not going to do that for this one. This is just more to demonstrate how we can use the same skeleton of the code, change a few things, and fit a different model. Because, right, if our goal is prediction, we just care how well the models perform. We don't even really mind how they work. So the only difference in this time we're going to call train, we're going to change the method to tell it to do a support vector machine, which is just another kind of machine learning model, and the tune grid argument, because, basically the all machine learning algorithms have different names for those tuning parameters. This time, a parameter called C in the support vector machine is the one that determines the balance between overfitting and underfitting. Apparently, if you look in the documentation, it tells you the smaller the value of C, the more regularization there is, and the less likely of overfitting, but more likely underfitting. Higher C will be a closer fit to the data, potentially overfitting. So that's the only, similar to the M-try. But again, you don't want to, there are default values for this, but I would say always look in the documentation and figure out what a plausible range of values for those tuning parameter is. Don't take the developer's word for what is the best default. You should always look into what people use for these tuning parameters before you do it. So the only way I determined that going from 0.02 to 1 in steps of 0.02 was a good value for C was by looking at the documentation for that model. But once again, everything here is the same as last time with train. I'm just setting a new random seed so we all get the same results. But the only difference is the method is now called SVM linear. That's a specific type of support vector machine. And our tune grid is different. And I got rid of the variable importance thing this time just because I didn't think it was important to show you that again. Other than that, so this is the same as before. This is the same. This is the same. These are the same. Only the method and the tuning grid are a bit different. So method is SVM linear, and the parameter is called C, capital C. The metric is still accuracy, and we're still using the same five-fold cross-validation as we did before. I'm going to highlight and run. It should take a minute or so to run. Then we're going to do the same as before. We're going to plot it to look at which tuning parameter maximize our accuracy, and then we're going to do a prediction on our test set and do a confusion matrix on it too. So let's take a look at the plot. We'll enter on this. Well, here again, you can see a certain C stands for cost parameter. Apparently, something around 0.3 is best. But once again, the y-axis doesn't have a ton of variation. It goes from a little over 92% to about 90%. But it's like, well, hey, SVM is a little bit better at predicting than random forest is. Maybe we should use it, There's really no harm in doing so as long as you feel you can defend that choice and justify it. And the more you understand about what the model is doing, the better. So, it would behoove you to read a little bit about what that model is doing before you actually publish anything based off of it, I think. And okay, next line, we're going to run do a prediction on the test data, and then our confusion matrix in line 117 here. So once again, it did quite well on the test set. It got over 93% correct, so it's a little bit better than random forest. And that's just to demonstrate that I just made some minor tweaks to the code, went in and learned a little bit about what is a plausible value for this C cost parameter, and then shake and bake basically. So that just shows you that this way approach is very flexible. And yeah, you don't have to stop there. You could try other models on the same data set by changing the method and making sure that you use the correct tuning parameter for the specific model that you chose. Yeah, so that is it for this demo. Yeah, the next one should be shorter, I think. So why don't we take a 10-minute break and come back at 3:17, and we can do a regression demo as well if people are still, right. You're only healed voluntarily, so if anybody wants to or needs to leave at any time, I will not be offended. But yeah, in 10 minutes I'll be back and do another demo. I'm gonna step out briefly, but then I'll be right back and can answer questions in the break. Thanks for your patience. So we'll start again in just a minute. Okay, so yeah, I'll just jump back into it here. We did a classification task so far, predicting a categorical variable, what type of variety of date we had based on images, measurements off of images. This time we're going to do a regression task, right? Our target, our thing we're trying to predict is a continuous variable. Now I know you all do not do crop breeding like many of my ARS scientists do, but that's why I do this example is sugarcane yield prediction, because that's like what they all spend all their time doing, is trying to figure out how much sugar you can get out of a particular piece of land, and which type of sugarcane is best at that. There's a lot of money to be made there. So yeah, and that's a continuous variable, right? The number of like tons of sugar per hectare is our target variable we're trying to predict. Yes, tons of sugar per hectare is our target variable, and people are interested in whether we can kind of, obviously you could go ahead and harvest all the sugar cane and process it into sugar and measure the yield, but people want to sugarcane is a perennial crop that takes several years, has a several year cycle that it's on, and it could be beneficial and save a lot of time in the breeding process if you could take a picture, a multispectral image, by flying a drone over the field, take a picture of basically of the leaves of the plant while it's still growing. And if there's information in that that can be used to predict yield later, we could save a lot of time, money, and resources in breeding sugarcane. So this is some real ARS data. I didn't get it from a machine learning competition website. I got it from an ARS scientist. I threw in a little random noise to, anonymize the data. So yeah, what they did was planted a bunch of different varieties of sugarcane. We're trying to see which one is the best at making sugar. And they flew drones over the fields and took pictures with a special camera that measures a bunch of different wavelengths of light, basically reflecting off of the plant. And you can use these wavelengths in different combinations to calculate different indexes, which are sort of like different ways of saying like how green the plant is, or what color, what is the quality of the light coming off of that plant. And that is thought to be correlated with kind of the overall condition of the plant, which may indicate how much sugar it can make. And there was different varieties and different treatments in this study, but I've gotten rid of that data just for example purposes. And the only thing we have is a rep column saying what experimental block, what part of the field each row of the data comes from, as well as information on the yield and the different the predictor variables being the different light wavelengths, and vegetation indexes calculated off of them. What kind of machine learning model are we going to use to predict sugarcane yield from this imagery measurements? We're going to use a lasso regression. That's just basically linear regression with a twist. It is just like a multiple regression where we have a bunch of continuous predictors to predict a outcome, but there's an extra term that includes a regularization parameter in the regression equation. And if you remember from a few minutes ago, regularization is how we determine the balance between underfitting and overfitting. And it, in this case, is called lambda. Well, the bigger the lambda, actually in the other ones that we've done, the higher the parameter, the more overfitting. But here, the higher lambda, the stricter the regularization, the less overfitting. The more, basically, the higher lambda goes, the closer those regression coefficients get to 0, or they even drop out of the model entirely. So like if more of your regression coefficients are closer to 0, you're not going to be fitting the data as closely. You're going to be potentially even underfitting. So, right, you want to balance between a model that is simple, doesn't fit the data, training data too closely, and not as closely as a standard linear regression. You want it not to be overfit, to be simple and make better predictions on the test data, but also not to be underfit. We want it to still, if there is signal in the data, not to miss it. We want to find the lambda that hits the balance, just like we did every other time, except now we're doing regression and not classification. Okay, so here we're going to import the data and take a look at it. We're going to read it from the CSV from the website. Let me see. Let me make sure that I have that on the worksheet here. Yep. So I didn't put the URL in the worksheet, but if you scroll up, it should be everything except the name of the CSV. So I'll copy that. Oh, whoops. We also want that data sets part. I'll put this in the chat momentarily. And yes, so I'll just copy that line if you want to paste it into your code. So I'm gonna hit Control Enter and run that line to import the data set from the web location. So it's a pretty small data set compared to what we had before. It only has 144 rows and 20 columns. A column for replicate, a column for the sugar yield, tons of sugar per hectare, and the rest of the columns are predictor variables. Okay? What are we going to do? This line of code says, give me the name of every column that is not TSH or rep, the yield or replicate. We're going to get 18 names, the names of the columns that are not the two that the replicate and the one we're trying to predict. Hit Control Enter. This code here, I won't get into how it works, but basically it is creating a scatter plot of every predictor variable on the x-axis and yield on the y-axis, and throwing a just kind of a locally weighted regression on top of it, just to give a quick visualization. Is there any signal here? Are any of these variables doing anything to predict yield just by looking at them one at a time? Let's take a look. Scatter plots, and then this line of code will print out that matrix of scatter plots or print out each scatter plot in kind of a matrix in our plot window. Here we go. So let's take a look. Well, yikes. Here we go. So to be honest with you, not that many of them seem to have any relationship. You know, some are completely, this particular variable is not correlated at all with yield. Although it's like, okay, some of them, maybe if you squint, there's kind of a weak positive relationship with many of these. You know, some are, some increase as some of them increase, yield maybe is weakly increasing a little bit as well. So I was like, well, maybe there's a little signal here. And plus, our model is going to combine the effects of all these variables together. So, you know, maybe we can get more power than just looking at any one of the variables at once. It's worth a try, right? So what are we going to do? Let me go back to the slides here. Let's take a look at how correlated some of our predictor variables are with each other, the same way as we did last time by creating this Pearson correlation matrix of all the predictor variables, each pair of them, and then making a heat map showing if they're correlated. We'll use the core COR function, and we called the sugarcane predictor variables is what we named that vector of variables. So I'm going to paste that name in there, and then run this to make the correlation matrix. 18 by 18, because we have 18 predictor variables, and then I'm going to make that correlation heat map with the GG core plot function. You can see that many of them are highly correlated with each other. Dark red indicating a high positive correlation between many pairs of variables, because these different vegetation index are all kind of like different combinations of the light from, they're sort of recycling the same information. So many of them are correlated. We probably have more variables than we really need to predict here, but I'm going to leave them all in. Instead of getting rid of any now, I'm going to leave them all in because we only have 18, and our lasso regression is actually going to do regularization and prevent overfitting even if we have correlated variables in, just to see what will happen. I'm going to leave them in for now because we just don't have too many. It's not a big data set, so there's no real worry about the model taking too long to run or anything. It is only a few rows and a few columns. Okay, now I'm not going to do an initial training test split either because we have such a small data set. I'm going to use the whole data set, but I'm still going to use cross-validation. Now remember, we have experimental blocks here. It does not make sense to randomly split up the cross-validation folds. We want to manually say, okay, just like I forget who was Bharat was asking earlier if we could like use data from trial 1 to predict trial 2. That's kind of like what we're doing here. We're going to split up the data, have 6 blocks, so we're going to do 6-fold cross-validation. Use the data from 1 through 5 to predict 6. Use the data from 1, 3, 4, 5, and 6 to predict 2, and so forth. So we're going to manually specify those cross-validation folds. And this code will do that. So this CV folds line will manually, it will create a list from 1 to 6 with the row numbers for the data points that come from block 1, then the ones that come from block 2, and so forth. And then for our cross-validation spec with train control, we're going to say, okay, we're going to do CV cross-validation, 6 folds, and the index out is specifying how our folds are split up. We're not going to do it randomly. We're going to do it with this pre-specified split, because it's not good to split your blocks up irregularly among the cross-validation folds. You should have an entire block in each fold. That's what we're going to do. So we're going to do, let me see, the map function to apply this function to each number from 1 through 6, and we're going to say sugarcane $rep. So saying for each number 1 through 6, which rows come from that rep. And then we're going to do our train control, telling it to do cross-validation with 6 folds, and we're going to use this CV folds object we just created to tell it how to split them. We'll run that code by hitting Control Enter, highlighting the whole thing. Okay, we're getting to the home stretch here. Just a little bit more code today, and then you can all go home. But we're going to do a lasso regression now. Again, we're going to use train because that's the function that is very flexible and can be used for all kinds of machine learning models. Instead of using the formula argument, we're going to say an X and a Y. X is our data frame with all the predictor variables in it, and Y is the vector, just one column from the data frame with the thing we're trying to predict. The method is glmnet because that's the name of the package that has lasso regression in it. So that's what we're going to use. And we're going to standardize our predictors just like before. We're going to do a bunch of lambda values by orders of magnitude, and we're going to set alpha equals. There's another tuning parameter in this type of regression model called alpha, but we're just going to set it equal to 1 because if we didn't, it would be a different type of regression. It wouldn't be lasso regression anymore. You can in the homework exercises, there's an exercise that lets you change that as well. Now the loss function we're going to use is root mean squared error, the square root of the average squared difference between the prediction and the truth. Obviously, the lower that is, the better, right? The smaller the error is, the better. RMSE is what that's called, root mean squared error. And then we're going to use our train control argument, passing the predefined cross-validation folds we just created that are based on the blocks. Right, so we want to train, we want X is basically select the predictor variables from sugarcane. The Y is the tons of sugar per hectare column. glmnet is our model. We're going to scale and center the variables. We're going to use only alpha equals 1. We're going to use a bunch of different lambdas and RMSE and use those folds we created. And then we're going to train our model. So let's enter all that in. So the sugarcane $TSH, that is the tons of sugar per hectare. We're trying to predict and see which one predicts the yield the best. glmnet is the name of the package in which lasso regression is implemented. And tune grid, I think we use the, what did we use there? The expand.grid function to put all combinations of those predictor variables, although there's only one alpha, and this one is called lambda. We're going to minimize the root mean squared error, and we're going to use this CV underscore spec underscore sugarcane we created before to tell it what folds to use. Any questions there? Okay, so we'll run this, making sure to also run the part that sets the random seed before we so that we all get the same result. And yeah, it just takes a few seconds because it's a simple algorithm on a small data set. So how did we do? First of all, let's go ahead and plot the model's performance relative to the value of the tuning parameter we picked. Here's the root mean squared error by cross-validation, and here's the regularization parameter on the x-axis. Well, this value of lambda minimized the root mean squared error, so here lower is better, so that's the minimum. But you can see that none of it is very good, right? We have, we're off by, at best, 5.4 tons per hectare, and at worst, 5.7. So, you know, if you go into the data, I think, yeah, if we look at the head of sugarcane, TSH, yeah, there, you know, the data are values like 25, 22, 15. our error is we're off by 5 or 6 every time. That seems pretty bad. Like the data only varies by 10 or so at most, and our predictions are off by 5. That's not very useful in practice. Like you're off by 5 tons. I mean, that's not very good. So at best, we didn't really, I would say, predict too well with this. But again, we had a very small data set, and we didn't really have any good signal in it. So it didn't overall, it didn't predict very well. But regardless, I want to just go through some of the next steps you do to investigate the output of this model a little more. And I think it's almost nice to use an example that doesn't work very well, because in a lot of these machine learning tutorials, they give you artificially fake, clean examples that work really well, that give you an overblown idea of how well machine learning models work. But, garbage in, garbage out, right? If the data don't have a signal you can latch onto, no model in the world is going to predict anything, because all that's in there is random noise. There's nothing you can get out of it. So this is just an example of that. So the best tune element from the fitted model is the optimal value of the tuning parameters that minimized cross-validation error. And if we just type the model name into the console and hit enter, it'll give us the prediction performance for all the lambdas, all the tuning parameters we tested. Let's take a look at what happens when we do that. So if we look at best tune, we'll enter. It says the alpha equals 1. Well, that's the only one we tested, and lambda equals 0.01 was optimal. And if we just type TSH underscore lasso underscore fit, hit enter, it will give us the root mean squared error for all the lambdas. And you can also get an R squared from these lasso regressions. You can see that the R squared isn't great. It's 0.3 for any of them. But then by the time lambda got really big, you're really underfitting and the R squared goes down. But for all these values we tested, the R squared is around 0.3. And there's the mean absolute error, which I talked about before. Instead of the square root of the squared error, it is just the mean of the absolute value of the error. Again, it isn't great for any of them. Okay, so inside of our fitted model object, there's a object within that called final model. That was the final model fit to the entire training set after we had optimized the parameters with cross-validation. We can actually, this code, it's a little bit involved, but what it basically is doing is we're pulling out what are the slopes, the coefficients from the regression model that was used with the best lambda parameter, and then it pulls that out. And then I also made some code to compare the slopes we get from lasso regression, and then I just fit a simple linear regression to the same data without any of this machine learning stuff, just a simple linear regression predicting tons of sugar per hectare from all these variables and compare them. Just as a proof of concept of what the lasso regression is doing and how it's different from a standard linear regression. And I've we want to do coef to get those coefficients from the model. Coef. So we'll run this code to pull out the coefficients from the best lasso regression model we had. Let's see, did that work? Warning message. Hopefully this works here. Oh, whoops! I left out the I left some blanks in there. The lambda is the name of the column we want, so I'll type that in there as well. Now, when we run this, it will work.
You're still missing one.
Oh, yep, I put another blank. Hey, thanks. I don't know why I even bothered with that, but there you go. Excellent. And now this will fit a linear regression model that is basically the same as that lasso one without any of the fancy machine learning stuff. Yes, we've been at this all day, so I'm kind of missing stuff here too. And then this is just a table to the best underscore coefficients rounded to 3 decimal places, and then compare it to the unshrunken ones. So Lasso is doing a shrinkage, pulling them towards 0, and this one is like the one from the standard linear regression. Let's take a look at them side by side. So you can see that if you look at anything except the it's not doing any shrinkage on the intercept. They're the same for both models, but the all of them are well, almost all of them are a little bit smaller, closer to 0 in the lasso regression compared to the standard linear regression. Some are substantially closer to 0, like this minus 0.8 versus minus 3.2. So lasso is not fitting the data as closely as a standard linear regression. It is regularizing, it is shrinking and saying, okay, I'm going to predict a little bit less well on this data set so that I can do a better job in the real world. That's kind of like machine learning in a nutshell. Again, here we did not, and Lasso can even make some go all the way down to 0 and just drop out of the model entirely. So it's actually a decent way to do like variable selection kind of stuff you can do with the Lasso regression instead of using information criteria like some people do. Anyhow, in this case, I would say, okay, let's not, take this to the big time. This exercise kind of demonstrated, this is like I did this with the real data and told the scientists, look, there's no signal here. Like we cannot use, these images are not valuable for predicting yield. Like it's not worthwhile to put a lot of energy and time into that because there's just no, whatever the yield ends up, that information is not contained in a picture you can take from a drone a few months before the harvest. It just doesn't, the information is not there. So yeah, that's useful to know, right? And if it were, we could make lots of money and go sell it to Domino Sugar Company and stuff, but we can't. So yeah, that was the lesson we learned there. So I think I have a wrap-up slide or two. Yeah, again, I would not deploy this model in the field. Yes, you could be like, okay, let me try another, maybe Lasso is not the best. I'll try a different type of machine learning model on this. But again, if there's no signal there, the best model in the world is not going to save you. Yeah, if you go into the slides, you can, there are some links to very good learning. Like if I had to read one book on machine learning as a beginner, I would read Introduction to Statistical Learning. It's a really great, that's how I learned a lot of this stuff. And the people that wrote it invented lasso regression and are very familiar with machine learning techniques. And so it really explains how stuff works. Like I would definitely read that if you're interested in going further with this stuff. By Hasty et al. And so there I have a link to that in the slides and a couple other tutorials and ebooks there as well. Oh yeah, and this book is freely available as a PDF online. So that's a nice thing too, and has examples in R. Yes, so that concludes all the material I have for today. I'm going to stop the recording and stop the screen share. I'll stick around for a minute if folks have questions, but if not, we will start again at 9:30 Central tomorrow, doing some omics stuff using some of the same machine learning principles we learned today.